Good. All right. So let's talk about superposition today. Well, we're going to actually do two things. We're going to continue on with the 2D separation of variables. We went through a problem last time. We got to the point of finally having a solution and showing how we could plot it and looking at, right, we have a relationship between the number of terms and the accuracy of the solution. And I do want to point out, right, we're solving for these TI solutions. If you remember from last time, we have TI equals CI something, right? Each of those TIs is it's not a temperature at a particular location, right? I does not indicate like a numerical node in the solution. Those are terms in the series, right? And that whole setup gives you one temperature at one location, X, Y, right? So you're compiling all this stuff together not to get a full solution over the space, but a solution at any given point X, Y. Right, so that's why we need to add additional terms in that equation in order to get better accuracy. Is just adding accuracy to the temperature at that one location. Okay, so right, so what I said was we went through and got that solution, but now we want to maybe go through an example that's slightly more complicated because we were really lucky in the last example, or I guess not lucky, but intentional, right? We said this boundary condition over here at t equals 0, or at x equals 0 is 0, temperature is 0. And over here, this boundary condition was q dot equals 0. Well, that's homogeneous in the x direction, which is what's necessary for superposition. But where are you ever going to find a problem where temperature is 0 on one side and it's adiabatic on the other, right? It's a really pathological case. And so we want to actually make this a little bit more realistic, and I'll show you how to go through the steps to solve it. So first, what we're going to do is we're going to look at this problem, right? So here's our problem on the left. This is what we did last time. Today, what we're going to start with is this problem on the right. So now we have, note instead of T0, we have T infinity. On the right-hand side, we have a convection condition. We have flux on the bottom and temperature on the top, right? And none of those things are 0. So what we want to do is let's go through and solve this problem using 2D separation of variables. And I'll show you two techniques that we can use to deal with the non-homogeneous boundary conditions in the different directions. The first one's pretty straightforward. It's just using transforms to get a homogeneous problem in one direction. And then the other one is actually just kind of a long-winded way of doing the problem. You just break it up into two problems that are homogeneous and solve them both and then add them together. Okay, so let's start with the kind of more straightforward one. So like I said, in this example, we have these boundary conditions. If you look, none of these directions are homogeneous. We have something going on in all of the directions. So our challenge is, let's get this to be a homogeneous problem in one direction and then solve it. Okay, so let's start by, we're going to start by writing out the boundary conditions for all of these things. So let's see here. Up in, first let's write out the PDE. So the PDE for this problem, it's the same thing as it was before. We're not adding generation. We don't have convection inside the domain that we're looking at or anything like that. So the PDE is the same as it was before, which was d squared t dx squared plus d squared t dy squared partial is equal to 0. It's the same PDE as it was before. Where we end up being different is looking at the boundaries. So let's write out our boundary conditions. So our first boundary condition, let's look at x equals 0. All right, at x equals 0, what do we have? We have t is equal to t infinity. Okay. At x equals w, we have, let's maybe help ourselves a little. We have let's draw a control surface here, right, on the boundary. So right on the boundary at x equals w, what do we have, say, going into this control surface? We have conduction. Okay, so going into that control surface, I have conduction minus k partial of t with respect to x. Sorry. partial of t with respect to x evaluated at x equals w is equal to what? And what's happening on the right side? Again, let's draw this. Be careful how we draw our arrows here. So we have something coming into the surface on one side. Just a few atoms to the right, we have something else happening. That's convection. So on the right-hand side, we have h bar times what's the temperature at x equals w, T at x equals w, minus the convection temperature to the surroundings. That's our second boundary condition. Right? And note, this isn't, neither of these are homogeneous so far, right? We have, in order to be homogeneous, we have the temperature and its derivatives have to be on one side. Everything else has to be on the other side. If what everything else on the other side, if that's zero, that's homogeneous. If there's anything else going on, T infinity, in both of these cases, or h bar times T infinity, it's not homogeneous. Okay, so that's the x direction. Let's do the y direction. In y direction, what's going on at y equals 0? Again, we can sit here and draw a little control surface. Okay, so coming into that control surface, we have q dot, which is a specified heat flux, q dot double prime. And it's going, I guess we're drawing this in the positive y direction, so it's a positive q dot. And then what's leaving? That's conduction into the body. What's leaving that surface? So that becomes minus k partial of t with respect to y at y equals 0. Right? Again, not a homogeneous boundary condition, right? Derivative of temperature is equal to something, not 0. Okay, last boundary condition. This one's easy. T at y equals h is equal to th, not homogeneous. Okay. So let's see. What we want to do then is let's find a way to get this to be a homogeneous problem. So what's one thing that we could do? Well, we could define a new variable, and let's call that variable theta. Let's say we're going to define theta. And let's make that variable something convenient so that what comes on the right-hand side of some of these boundary conditions ends up being 0. So we could say that theta is equal to the temperature T minus T infinity. Okay. So if we note, right, we're still saying that theta is a function of x and y because T is a function of x and y. But it's relative to this T infinity here, that is a constant. So if we make that substitution, let's move on to the next page here. So let's make that substitution and go through and restate our boundary conditions again. Okay, so if we make that substitution, the PDE becomes, substitute theta in for T, and you take the second derivative or second partial of that constant, that goes away. So it just becomes partial squared of theta with respect to x plus partial squared of theta with respect to y is equal to 0. So now we have this PD in terms of theta, our new variable. Our first boundary condition, see if I can kind of scroll back and forth. So our first was t at x equals 0 is equal to t infinity. Okay, so this becomes theta at x equals 0 is equal to 0. Right? So we're taking now this problem with respect to, or with reference to t infinity. So if we're forcing that to be t infinity at the boundary condition, then it's 0, right? So now we just created a homogeneous boundary condition at x equals 0. Okay, 2, the second boundary condition was at x equals w. So this becomes minus k times the partial of theta with respect to x, evaluated at x equals w is equal to, scroll back up a little bit. Okay, so is equal to h times t at x equals w minus t infinity. So we substitute in theta, and we just have now theta evaluated. This is now theta at x equals w times h bar. Okay, this is now homogeneous, right? D theta dx is a function of theta. And what's on the right-hand side is also a function of theta. So there's nothing left over that's not directly related or multiplying theta. So this is now a homogeneous boundary condition. Okay, so through this transform, we've just created a homogeneous situation in the x direction. All right, that's really all we need to solve it. So we can continue on, but let's actually just finish with our little transform here. So then in the y direction, the flux in at the bottom becomes q dot double prime is equal to minus k times partial of theta with respect to y, evaluated at y equals 0. Okay, and then for t, so theta at y equals h is equal to th minus t infinity. We have to kind of switch things around there. Right? Okay, so y is definitely not homogeneous. Right? We still have q dot on one side and we have th minus t infinity, but like I said, this is now a problem that we can actually solve using separation of variables. Question? Y is too homogeneous because in order for an equation to be homogeneous, we need anything that's a theta or that variable on one side of the equation, or let's see, so we could bring this, let's do this way, minus equals 0, right? So can you see now we have theta is there, it's multiplying h, we have d theta dx multiplying minus k. There's nothing left over that's not directly multiplying theta. There's no t infinity or anything like that. So it's equal to 0, so that becomes homogeneous. Good question. Okay. Anything else before we move on here? Yeah. If this over here, let's say, was equals, sine x or something like that. No, that's not homogeneous, right? Because anything on the right-hand side that's not directly multiplying theta or in any of its derivatives, that counts as sort of the other part or the non-homogeneous. So you could have any function of x on the right-hand side. This up here, let's say this is actually just t infinity over here. That's still technically a function of x. It's just x to the 0th power, right? So it sort of falls into that category by technicality. Let's see. Okay, let's go to this. Okay. So we have done our transforms and now we can restate the problem. Okay, so now we have our mathematical statement of the problem in terms of theta, right? And the next thing is we can then proceed with separation of variables as we've done before, as we did last time.